All right. Hi, everybody. So it's 8 p.m. somewhere in London. So 9 p.m. in the rest of Europe. Well, at least where I'm and Kenny is. And I know it's 7 a.m. in somewhere in Melbourne. So welcome everybody to this VSA online session. So today I'm happy to host Kenny Schlegel from Chemnitz University in Germany, and he will talk about HDC mini rocket, so the method for encoding time series. Before I leave the floor to him, I just want to make two announcements. The first one is regarding the panel session that is scheduled to the 19th of December on this online channel, and I am soliciting contributions. So the idea, I just want to vocalize it, so even for people who will watch this recording online or offline, the idea is that during this session, we share the ongoing work. So some ideas that are under development, not fully developed, even some outrageous ideas, and so that's kind of interesting to hear. So if you have something of this kind, so please drop me a line. So we will form a program for the 19th of December. Also, I so now want to vocalize a call for contributions for the next season. So I have already have like 3 confirmed talks for the spring session 2023. So more speakers are wanted, and so again, drop me a line if you want to present your work at VSAONLINE webinar series. That's it from my side. So I welcome once again Kenny Schlegel. So please, the floor is yours.
Okay. So I start sharing my screen. Okay, yeah, welcome also from my side, and thank you for the introduction and being here. The topic of today's talk is about HDC mini rocket, which means the explicit time encoding in time series classification with hyperdimensional computing. Before I start explaining the HDC mini rocket, I would like to give you the similarity between Per's last presentation and today's talk. So the last talk by Per was about visual place recognition, and for this visual place recognition, we used different local descriptors in an image and associate each vector with its position in the image. So to do this, we used the simple HDC mechanism of bundled role filler pairs, and doing it to incorporate it in an existing approach, and can beat the state-of-the-art method by doing this. And today's talk is about the time series classification, where we have a signal over time and also some feature vectors like L1 to Li, and want to associate these feature vectors at a specific time step with its position in time. And we are also using the scheme of bundled role filler pairs for also this time encoding mechanism. So we can say we use HDC in both approaches to systematic incorporation of model knowledge. And this is, it can be done very easily with the so-called bundled role filler pairs in the VSA domain. Okay, let's talk about the HDC mini rocket. It is mainly, or the HDC mini rocket and today's topic is mainly based on the publication which we published this year on the IJCNN conference, and it is a joint work together with my colleague Per Neubert and Peter Porzel. And the rest of the talk, or almost the rest of the talk, I would like to explain the paper, what we did in the paper, and how it works and why it works. Okay, as you have seen, the title is HGC Mini Rocket, and yeah, it has something to do with time series classification and hyperdimensional computing. First, I would like to say something about the time series classification and why do we something with time series. As you maybe already know, we are working with mobile robots or in general with autonomous systems. And such an autonomous system has, for example, different sensors. And each sensor produces different outcomes or different values over time. And these, as you can see, are time series. And based on these time series come from different sensors, we want to solve different tasks. For example, we want to recognize like a critical state of a robot based on its sensors. Or from an automotive perspective, we want to recognize known driving scenarios in like urban driving scenes. So imagine each object in a traffic scenario also has a position and velocity over time, and these are also some time series which we can use for classification, like known driving scenarios like turn lefts, turn rights, overtaken, cut-ins, and so on. And since we are using different sensors and different sensory values over time, it is related to the multivariate time series classification domain, since we have multiple sensors per time step. And that's why we are working on multiple time series. We did some literature research on the state of the art within this domain. And there we found a benchmark paper based on the multivariate time series classification. And in this benchmark paper, they are using a multivariate benchmark with 26 data sets, and they compared 17 different methods. And the result of this benchmark paper is that Rocket, the abbreviation for Random Convolutional Kernel Transform, shows the best trade-off between a good accuracy and high computational performance. And based on this Rocket, there is a superseded version Mini Rocket. And that's why we concentrate on this method Mini Rocket, because it is really fast and really accurate in the time series classification. Since Mini Rocket is actually developed for univariate time series, and there's just a extension, or there's just an implementation extended from the authors for a multivariate domain. We also concentrate in the first step on the univariate time series classification. There's also a benchmark dataset ensemble with 128 datasets, and Mini Rocket is also performing well on those datasets. And as I said, we concentrate first on the univariate time series domain, since Mini Rocket was initially developed for the univariate domain. And all those datasets from these benchmarks has a high variety on applications. So the domains are really diverse. So there are not only the robotics context, like for us from different acceleration sensors like IMU, but there are also some data sets related to like electrical biosignals, like EEG recordings, or audio, chemical concentrations, or spectrograms, and something else. So it's a broader range than we are using with our robots. So it's more difficult, and it's a good benchmark for evaluating a different or specific time series classification method. Okay, as I said, Mini Rocket is a good state of the art for univariate and multivariate time series classification. But there can be a problem with encoding of a time series. Imagine we have a simple two-class time series classification problem. It can be Gaussian noise, which is usual for real-world world data, and we have a single sharp peak either in the first half or the second half of the signal. Here are some examples for class 1 and class 2. And as you can see, in class 1, the peak is in the first half of the signal, and in class 2, it's in the second half of the signal. And as you can see, there's a high dependency in time. So it's really important where the signal is in time. And if we apply mini-rocket on this problem and want to solve it with mini-rocket, then we have seen that in the standard case, mini-rocket reaches an accuracy of 67%. And we also create a more challenging case where samples from class 1 are similar to class 2 based on the encoding embeddings, and their mini-rocket only reach an accuracy of around about 57%. And keep in mind that random guess for this simple 2 class problem is 50%. So the mini-rocket is not really able to solve this problem quite well. So there might be a problem. But the question is, why does mini-rocket, or why is mini-rocket not able to solve this problem really well? To answer this question, we have to answer how does mini-rocket work? And so we have to go more deep in the mechanisms of mini-rocket. And I would like to explain it on several images, and starting with this. Our input signal over time can you see here. And mini-rocket uses different random kernel filters and convolve the signal with these random kernels. And for each filter, it uses different dilations to spread the filter over the signals and increase the size of the receptive field. So we have different filter dilation combinations, and if we convolve the signal with those filters, we get different responses. As you can see here, we have different responses over time for each filter dilation combination. Then mini-rocket uses an approximate cumulative distribution function to sum the responses over time. And to do so, it uses thresholds for calculating the bins of these distribution functions. And it means if we have a response, then we apply different thresholds and look, okay, is the value of the response greater than these 3 thresholds, then the resulting is either 1 or 0. And after thresholding all the responses, mini-rocket accumulates all the results, and these are the bins of the approximate cumulative distribution function. Concatenating the resulting bins to a vector is our embedding of the complete time series. And this vector representation can be used for classification with just a simple classification algorithm like a ridge regression. To see why it is not a good idea to accumulate the results over time, I would like to zoom in, or would like explain it in more detail. So as I said, we have our responses for each filter dilation combination and calculate the bins for the cumulative distribution function. Then we have a intermediate representation, as you can see here, with our binary values. So either the value is above or below the threshold. And then at the end is the accumulation. So sum over time for each of those rows, for each row. But the accumulation loses information about location in time. And that is very important to localize the feature in time if we have signals with a high time dependency, as we have seen in our synthetic dataset. So it is desirable to encode global time context before we sum up over time. And by the way, all the columns here are feature vector per time step. And in mini rocket, these are 9,996 dimensional vectors. So for each time step, we have these high dimensional vectors, and at the end as well. And it seems to be that our intermediate representation are still or are already high dimensional vectors, and maybe we can use HTC for reaching this goal of encoding global time context before we accumulate over time and loses the information in time. Here comes hyperdimensional computing into play. So as I said, we have our intermediate representation of binary high dimensional vectors for each time step. Then it would be nice if we can associate each high dimensional vector with a specific timestamp vector. And we can apply our VSA operation of binding to associate the feature vector with a timestamp vector and overlay with bundling, which is equivalent to sum up in mini rocket over time. But if we are using here our HTC, we are able to incorporate our global or our time. And as you can see, it's just the simple approach of VSAs, the bundled rule filler pairs. But it is very important how we create these high dimensional timestamp vectors. And it is desirable to have timestamp vectors which are nearby in time. They should be similar. And timestamps which are far away in time, they should be non-similar. So the goal is a graded similarity if we are going further in time. And this can be reached if we are applying the well-known fractional binding for creating a graded similarity of the timestamp vectors. What does it mean? We used fractional binding for encoding the time. So here on this figure, you can see different graded similarities for timestamp encoding. And it means we have our initial time step 0. And this is based on our seed vector. And we apply fractional binding on this seed vector following this equation here. It's well known, it's the equation for the fractional binding with Fourier transform and inverse Fourier transform, and we add an additional hyperparameter S to adjust the similarity decrease over time. So it means if we have, for example, S equal to 0, we have no change in time, so each timestamp representation is equal. And if we increase S, then the similarity decrease faster. So it means, for example, if we have S equal to 1, then the first and the last timestamp vector are completely dissimilar, and in between we are getting a curve or graded similarity like the green curve. So it means if we have our hyperparameter S and increasing this S leads to incorporating of more temporal context. And as I said, if we set S equal to 0, we have no change in these timestamp vectors. So all timestamp vectors are equal. And this is equivalent to the original mini rocket. So this is a nice property because with incorporating these timestamps with this hyperparameter S, we created a more channelable version of the mini rocket itself. By just, if we set S to 0, we have the original mini rocket, and by increasing S, we are incorporating more temporal context and add like a more degree of freedom to the mini rocket approach itself. Okay, now we have seen how we can incorporate the global time encoding in mini rocket with an additional hyperparameter. What is the result if we apply this HTC mini rocket to the synthetic dataset which I mentioned at the beginning? Now we have seen that mini rocket is not really able to solve this task, but if we apply HDC mini rocket, which uses the global time encoding, then it is able to solve the task almost perfectly. So we can increase the accuracy from 67 and 57 to for both 94%. So it might be a good idea to have this possibility to incorporate global time when we are encoding a signal with a mini rocket. And to see why it works, I would like to show you the following figure here. It shows the similarity matrices for mini rocket and HDC mini rocket. So it means for the first similarity matrix, we have similarities between the vector encodings of the signal of class 1, for example, here, and the sample of class 1 here. And a bright pixel means there's a high similarity between both samples, and dark pixels means there's a low similarity. And as you can see here, there's a diagonal with the highest similarity because the same samples have the similarity of 1. But as you can see, there are some samples of class 1 which have a high similarity with signals of class 2. Since mini rocket is not able to locate the peak based on these accumulation over time. But if we have a look on the HDC mini rocket, we can see that the similarities between signals of class 1 and signals of class 2 is really low. So there is only the signals of class 1 are similar to each other, and signals of class 2. So by incorporating the global time encoding, we are able to group the signals based on its location and time. So it's just an additional visualization and to get a feeling about how it works and why mini rocket does not work, because we have similarities between class 1 and class 2. Okay, now we have seen how HDC mini rocket can improve the synthetic dataset example. At the beginning, I said there is a benchmark ensemble on univariate time series with 128 data sets. And now I would like to show you a picture where we reported the change in accuracy between HDC mini rocket for different scaling parameters and the original mini rocket. So on this image, you can see the dataset IDs on the y-axis and different scaling parameters on the x-axis. And the color indicates if a dataset is getting better or getting worse. So blue means a dataset is better for HDC mini rocket compared to the original mini rocket, and red means this HDC mini rocket with a appropriate scaling parameter S is getting worse. And as you can see, there are some blue rows and some red rows. So it means, for example, this row here, for this data set, it is getting better. And the opposite is here. Here are some data sets which are getting worse if we incorporate more temporal context and increase the parameter S. As an example for the positive and the negative influence of the parameter, I would like to show you those both data sets. So if we have a look on the data set which benefits from the parameter S, is, for example, this data set here. You can see some plots of the signals out of this data set. It is a data set which classifies hand trajectories, so motion data. And you can see that for each class, there's a specific starting point and a specific shape over time. So as a human, you can say, yeah, it makes sense to incorporate global time because, for example, in class 2, after the half of the signal is getting down to 0 and so on. So for such a data set, global time encoding helps. It was the blue row on the image before here. And a negative example can be seen here, where global time encoding does not help and makes it worse. For example, blood pressure measurements. And as you can see, there are signals with high frequencies, with periodicity, and so on. And here it makes not sense to incorporate global time because it's more important to report the frequency or the amplitude and so on. And yeah, as we have seen, incorporating global time context in this data set here makes the accuracy worse. So these are two examples where global time encoding can help or global time encoding does not help, just as an example to see that it's really important to know if global time encoding can help or not. And yeah, since it is crucial to have the correct hyperparameter S, which adjusts the global time encoding, we need to find the optimal S for each data set. And to find the optimal S, we can use data-driven approaches for selecting the best S. For example, we can use an oracle. So it's like the best case we can reach. For example, we have our training data, and for each training data, we apply different parameters of S. And then then we have a look on the accuracies on the test data. And based on the highest accuracy on test data, we can say, okay, here on S equal to 7, the accuracy is the highest. That's why parameter of S would be the best. But in real world application, it does not make sense because we do not have ground truth. We cannot evaluate the method on the test data. That's why we did also some experiments with another data-driven approach, the cross-validation. So if we have our training data, we can split the training data set into different splits, different train test splits. And for each split, we can apply different scaling parameters, S equal to 0 and until S equal to 7, for example. And then we reported the accuracies for each split and look for the highest accuracy for each split. So it's like voting. So for example, if split 1 has the highest accuracy for S1, then we say, okay, split 1 votes for S equal to 0. And then we count all votes and select the winner and have our best scaling parameter for the global time encoding. And based on these two approaches, we got some results on the univariate UCR benchmark dataset. And it can be seen on the following bar plot. Here we reported the accuracy improvements compared to the original mini rocket. So it means, for example, a positive value, then HTC mini rocket is getting better compared to the original mini rocket. And blue means the oracle, so it's the best accuracy change we can reach. And orange is our simple data-driven approach for selecting the best S. And as you can see here, for example, dataset 48, which really benefits from these global time encoding, we are able to improve up to 27% if we have an oracle and which says, okay, that's the best S based on our test data, but usually we do not have our test data. That's why the cross-validation is a little bit below this maximum improvement, but it still reached 12% improvement compared to the original mini rocket. So it seems to be that cross-validation is a good way to find our optimal S if we do not have test data. So just splitting our training data and apply cross-validation to find the optimal S. Also, for some other data sets, it is beneficial to incorporate global time. As you can see here, there are some accuracy improvements, and yeah, at all we are able to improve 17 data sets out of this 128 when we are using this cross-validation, so the orange bars. Okay, now we have seen that we can reach some improvements on the benchmark ensemble for univariate time series, but what is with computing time, which is very important if we have some extensions of an already existing approach. And if we are looking at the inference time for each UZA data set, we can recognize the following behavior. This plot shows the inference time for each data set. So each blue dot in the plot represent one data set, and the X value of the point represents the inference time for mini rocket, and the Y value represents the inference time for HTC mini rocket. And it means the diagonal represents that both approaches consumes the same computational time. And it means if the blue dots on this side, mini rocket is slower, and if the blue dots on this side, HTC mini rocket is slower. And we can say HTC mini rocket is about the same computational effort as mini rocket. Only for some data sets, HTC mini rocket is a bit slower, but in average, HTC mini rocket is not significantly slower than mini rocket. Okay, a short summary. So we have seen if we are using a simple HTC mechanism, for example, the well-known bundled rule filter pairs, it is possible to improve existing state-of-the-art approach, like the mini rocket, in time series classification, which is similar to the results in visual place recognition approaches, as I mentioned at the beginning, which also use bundled rule filter pairs. And if you are interested in more details, I would like to refer to our paper, and based on this HTC mini rocket paper, there's also ongoing work, also together with Dennis Schlegel, and we are working together on different points. For example, we did some experiments on different similarity kernels for creating these timestamp vectors, so different created similarities for the timestamp vectors. And we also want to extend the HTC mini rocket approach to the multivariate domain. With combining the channels based on the VSA operations. And on the next slides, I would like to show you some preliminary results based on these 2 points, starting with showing some results on the different kernels. As you have, or maybe you know, for these fractional binding, you can use different kernel shapes. The basic kernel shape is the same kernel as you have seen on the slide before, where I introduced the creation of the timestamp vectors itself. But we can also use different kernel shapes like Gaussian or triangular shapes. And now the question is it helpful to not only fit the hyperparameter S, but also the kernel shape? And to evaluate this, we also reported a bar plot based on the plot before. So you can see it on this slide. So, for example, we are able to also increase the simple data-driven approach which has just 12% improvement. And if we add the degree of freedom for the kernel shape, then we are able to push up this improvement up to 19%. So it might be a good idea to not only find the optimal S, but also the optimal kernel shape. So for some data set, it's beneficial to use the zinc kernel. For some data set, it's beneficial to use the Gaussian kernel or the triangular kernel. And yeah, it also increased the average performance for the UZR dataset ensemble. Okay, the second point was also applying the HTC Mini Rocket on multivariate time series. And as I said at the beginning, there's also a benchmark ensemble with 30 multivariate datasets. And first experiments with just incorporating the global time encoding in the implementation of Mini Rocket for multivariate time series results the following bar plot. Here we see the 30 data sets from multivariate domain. And as you can see, here's a high peak for one data set. And it shows that we are able to improve this data set up to 73%. So it means if we incorporate this global time in Mini Rocket for multivariate domain, then it is able to solve this task not with 35%, but with 61%. So there's a high improvement for this specific data set here if we are using this global time encoding with HTC. And we can see that the cross-validation approach reaches the same accuracy as our Oracle. So it is also really interesting. So yeah, this first experiment shows that it is also beneficial to incorporate these HTC approach in Mini Rocket for this multivariate domain. And yeah, ongoing work is still there because we want to improve the channel combination itself based on HTC operations. So for now, it is based on the implementation for Mini Rocket, which uses randomly different channels and overlay them, and then apply the feature generation per time. Okay, these are two ongoing works based on this HTC Mini Rocket. But after publishing this HTC Mini Rocket, there's also some other work in the literature. So the authors also published some extensions to Mini Rocket. So for example, there's a superseded version called Multi Rocket and another version called Hydra. So as you can see, there's a lot of work in this time series classification, and the group of the Rocket family is still working on newer versions of this time series classification method. And to just explain shortly the key ideas of multi-rocket and Hydra, I would like to show you on this slide. For example, multi-rocket uses more pooling operation over time, not only these approximately cumulative distribution function. It uses the original data and the first order derivation. And the resulting embedding vector is the concatenation of all pooling results, which leads to a higher computational effort. And very important is that one pooling operator is the mean index over positive values. And this can be seen as a global time encoding because if we compute the mean of the positive values, then it's like a mean location in time of the features itself. But there can also be a problem, or there's also a corner case. Imagine if we want to compute the mean index of positive values of these two vectors, like over time. So these are the results of thresholding. So at time step 1, we we have a value of 1, then 0, 0, 0, and at the end we have also a 1. And for another signal, for example, another sample, we got the following result. There we have in the middle two 1s. And if you compute the mean index of positive values, then we got for both signals the same mean index of positive values, even if the peak is at different locations. So there's also, or there seems to be another problem if using mean index of positive values, and maybe there's also maybe it's also a good choice to replace these mean index of positive values with this global time encoding with HDC. And a brief overview of Hydra is that Hydra uses a dictionary approach, which is also based on these random kernels like MiniRocket, but these kernels are grouped. And for each group, a histogram is created with the highest response per time. So if we have our input signal here and different groups, for each group we have different kernels for control of the signal, and we apply each kernel on our signal, we got the results shown in this plot here for each group. And then we look for each time step, what is the highest response, and reported this kernel ID, and then create a histogram over time. So for example, we count the highest responses and say, okay, the red kernel is represented 4 times, the green kernel is represented 7 times, and so on. And here's also a really important point, because creating a histogram of over time is also losing the position in time of the specific response. So it's the same problem for Hydra as we have in MiniRocket. And first ideas to incorporate HDC in both approaches is for multi-rocket. As I said, we can incorporate this global time encoding as we did it in HDC MiniRocket to overcome the problems with this mean index of positive values. And maybe we can also use HDC for compressing the different pooling operations with bundling, instead of concatenating all the results together and got a really huge vector for classification. And it's maybe more efficient. For Hydra, we can also incorporate the global time encoding before creating the kernel winner histogram to overcome the problem of losing the information of time. And also creating the histogram can be done implicitly with bundling of kernel IDs. So if we have for each kernel a random hypervector, we can also bundle the highest responses, so the kernel IDs of the highest responses, and this is similar to creating histogram. But these are just ideas where we work on, and as I said, it's ongoing work, and for now we do not have some results which I can show. But one thing I want to show shortly, it's my last slide before coming to the summary. One extension, as I said, is multi-rocket, which uses a time encoding mechanism similar or somehow similar to the global time encoding. And if you have one look at the data sets of univariate time series where the global time encoding helps in HDC MiniRocket, their multi-rocket is not able to reach this high accuracy as we have reached with HDC MiniRocket. So it indicates that multi-rocket has somehow a time encoding mechanism, but it might be not that good as our HDC approach of global time encoding. And the same goes for the multi-rate domain. If we have a look on this very well performing data set 12 here, where we can improve the accuracy from 35% up to 61%, their multi-rocket just reach 38%. So it also seems to be that multi-rocket is not really able to incorporate the time very well by just using these mean index over positive values. So these are just just a quick view of some important results for now based on these extensions on mini rocket. Okay, now I will come to my summary slide. Based on mini rocket, we have seen that HTC time encoding can improve the accuracy for univariate and multivariate data sets, just based on the simple mechanism of VSA, the bundled rule filter pairs. Then we have seen that HTC time encoding prevents failure in corner case scenarios. Remember the synthetic dataset example, which I've shown at the beginning of the talk. So if we incorporate this time encoding here, we are able to solve this problem. And HTC Mini Rocket is about the same runtime as Mini Rocket itself in its original implementation. Some open problems and further work is or are one point is finding a more efficient timescale selection method. So is there a more efficient way to choose the correct hyperparameter S instead of running a cross-validation and have a high effort in training? And another point is, can we also using relative time encoding in addition to the global time encoding? So if we have different feature vectors and just encoding the relative time between the features. And last point is, for example, if we compose hypervectors and using these composition like a bundle, if you are using this bundle for classification, then sometimes the bundle is too noisy for classification, so the classifier suffers from bad features in this bundle, and that's an open question, how if there is a possibility to denoise a bundle for appropriate classification or appropriate classificator to reduce bad noise and increase the accuracy at the end. For example, if we apply such a bundled rule filter pairs. And I'm at the end of the talk and open for some questions.
Thank you, Kenny, for your presentation. So now I open the floor for questions. Anybody? Please unmute yourself and speak. Maybe I can start with a simple question to begin with. This parameter S, which I guess in fractional power encoding has a term of bandwidth. So if you talk about FHRR complex representations, what is the range of values in your case? Yeah, I mean, so you presented S, so like from 0, ranging from 0 to 7, and I guess maybe even beyond. But I mean, is there any limits on S?
Actually, there are no limits on S, so we can increase it up to a specific value, but then we are ending in a really sharp peak here. So it's a really fast degradation of similarity. So that's why we are ending at the parameter S equal to 7. And choose the range 0 to 7.
Because in FHR, well, you work with HRR, so with real valued vectors.
Yeah, we are working with real valued.
But I mean, the FP encoding assumes first doing what is it, the Fourier transform. So you put it in the complex field, and then I mean, if you do it, I mean, use the same parameter in the complex field, so it just adds a little bit to the phase. So I mean, it's always kind of, I mean, the phase is limited. of the of each component. So it would be interesting to see whether it really can be like any S or.
Yeah, for now, I would like to, or I would say that's actually possible for any.
Maybe there is a kind of modular operation during this transformation to complex and backwards.
You mean here?
I think here is the thing that once you do S, I mean, S is basically exactly your bandwidth. And so what Kenny was saying, as S is increasing, you're essentially ending up with delta function kernel, which means that any timestamp is going to be unique, which might be pretty bad because you don't have any aggregation of the information. While I mean, obviously, S0 is the other way around. There's no like discrimination at all. But then it's pretty. This is intuitive. This is averaging sort of sum. While going to large S is just most likely going to be not useful because any sort of relative shift in this time sequence is going to result in a completely different representation.
Then another thing, more of a comment. I don't know if you agree with me or not, but I think I mean now it's the right time to kind of clarify the terminology. So especially when working with time series and these methods like mini rockets or stuff. So I'm thinking about the term of kernel. So here you use this term in two different contexts. So the kernel for which is approximated by a given by given FPE function, and the kernel is a filter that kind of that is tried through your time series, and these are two different kind of things. So maybe and both of them they have meaning in their domains, but I mean maybe in our context we need to be careful with the terminology a little bit, not to mix up.
That's right. Yeah, I didn't recognize that. It's more like a filter for when speaking about a kernel for the time series itself.
Yeah, it's a different. Yeah, it's a filter. Yeah, and here, for example, on this slide, so this is a different meaning of kernel.
Yeah.
Anybody else?
Question.
Yeah.
Okay. Ross, go ahead.
No. Yeah, I just wanted to say, Pentti, please go ahead.
All right. Do you use permutations? I didn't see you using permutations. You just use it multiplication and addition. So that's my question: is what?
Yeah,
if you have experimented permutations, and what have you found out?
For now, we did not permutations because we want to create these global time context with these created similarities. If we are using permutations, then these vectors are completely dissimilar, and we are also just creating these n-grams, so bigrams, trigrams, and so on. And in that case, we just want to encode the complete time series with these manually designed timestamps or timestamp vectors itself. And permutations with like n-grams, I guess you mean like that, is somehow related to encoding relations of consecutive time steps.
So we have found out that computing n-grams for small n, fairly small n, you can use permutations, and so your whole thing sort of becomes like sums of products of permutations, and just the n-gram, it just captures a little bit more than a single instance. just capture sort of, and how those are located in the whole thing, then I just know that the math of sums of product of permutations is very interesting. So you might be able to use it. And I want to say one more thing. Ross is the one who convinced me of the importance of permutations. So Ross, go ahead.
I was going to say, well, a range of things as usual, but at first glance, working within the constraints of what Kenny and co have been doing. Hi, Kenny. Thanks for a great talk, by the way. I wouldn't have thought there was that much need for permutation. However, heading where you were heading, Pentti, if you're interested in combinations of features, so essentially n-grams, then it may well be necessary. I know, I mean, Kenny, you were mentioning some of your open questions there. One of them was on time differences, for example. So rather than the significance of some feature being precisely where it occurs or roughly where it occurs in the time window, you're more interested in the time difference between different features occurring. So it might be, you know, a good marker of the classification you're interested in might be that feature B follows feature A by so much time. Off the top of my head, I think one way you might be able to do that would be if you, at the moment, what you're taking is you're taking each of the feature vectors, and you're binding it with the timestamps, and then effectively you're bundling that at the end. If you were to, in addition to that, take all the feature vectors and bind them with the multiplicative inverses of the timestamps, bundle all those together, and then bind those two together, I think, because fractional power encoding is not really I'm not that good at it yet. I think that if you're binding what you get is a term which corresponds to the binding of the timestamp with the inverse of timestamp, I think that will get you a representation of the difference in the times between the two timestamps, if you're using FPE. Yeah. And then the other thing you'll get bound with that is the binding of the two features, A and B. So that might be a way of doing that. But to the extent that the features A and B are similar, they may cancel each other out. So you may need to use permutation in that to sort that out. But yeah,
I just wanted, Ross, I just wanted to complement what you said. I think it really depends on the underlying method for detecting features. So this one is, I mean, Kenny presented for mini rocket. So I remember, well, a long time ago. So I think one of early Dennis works was within our project on analyzing car passages and classifying cars. And there is this kind of one of standard signal processing methods of detecting peaks. So you have a pre-processing of a signal. So and then but it assumes that the signal has certain shape, and which is consistent for a given class. And then, of course, so first you identify useful signal, so kind of filtering from the noise level from the floor, noise floor, and then within this useful signal, so you may identify like features, you know, and then you can encode them using permutations or whatever, is like really in VSA manner, and then it helps. So it works in this way. But I mean, here we deal with different signal processing or feature extraction method in time.
Yeah. Yeah. I think that I think the distinction here again, yeah, I mean, in classical signal processing, you'd expend a lot of effort on trying to pre-process your data to extract out the features which are strong signals of what you're interested in, and try to suppress the other features as noise. Whereas if I understand what Kenny and co are doing here, is they're effectively using the random Fourier features approach. So they're sort of using the math of the complex valued representations to basically say, create automatically, here's a whole bunch of features, some of which may be useful, some of which may not. And that might be partly contributing to the point Kenny was making about if we bundle too much stuff together, maybe everything gets submerged in noise. So if that's the case, maybe that's an argument for a separate pre-processing stage. But at the moment, I think that, and I will stop in a second, Kenny, I think at the moment that what they're doing is by relying on the random Fourier features thing, which comes out of the complex valued representation, they're essentially treating it entirely as, I'm just putting in this scalar value which varies over time, and I'm going to rely on the maths to create a whole bunch of useful features, some of which may be helpful, most of which probably are not. Sorry, I'm going to stop now, Kenny.
Yeah, thank you for your comments. So maybe something based on your first comment you said, based on these FHRR. So if we bind the inverse, the inverse of the position encoding, then we got the pairs of the positions itself, so the relations. So you said, right? If we are using these FHRR.
I think that's the case. I think if you, let's just say you had 2 timestamps.
Yeah.
I think if you bind one timestamp with the inverse of the other, I think that would get you a representation of the difference in time between the 2 timestamps.
Yeah, that was a thought some weeks ago, some month ago. So using these properties of HRR and fractional binding and unbinding in these FHR is like creating the difference between these vectors. But first experiments show that it ends up in too much noise, and because you create pairs with each time step, so time step 1 with 1, 1 with 2, and so on. So we have a lot of pairs actually.
Yeah, I think, if it's, it'd be worthwhile. That was just off the top of my head, so I've got I'm certainly not making any kind of strong claim that would work. I would first just look at the maths of it and do some simple experiments just to see if it works. Actually, does it actually calculate for you a representation of the difference in time? Yeah. Because if that is the case, as you say, if you're just binding a bundle, then you get all across, binding 2 bundles together, that will get you all across pairs. But if in fact all the cross pairs which have the same time difference between them map onto the same difference representation, your number of effective pairs is much lower. It's only down to the number of unique differences that exist. So I think with most of these things, they tend not to work when the first time you try them. So I think it's worth some detailed thought and experimentation to see if they don't work because they truly don't work, or they don't work because of some technical thing which has been temporarily overlooked.
Yeah, I also think it's a good way in this direction. So
could I make just one other point here, which is about your use of those data sets? I think it's, and this relates to all the stuff which has been discussed so far. I think the tendency is for people when they're looking at data sets to think, oh, this is real data, so this is important. Whereas synthetic data, well, I can use that to do these little things, but I'm really interested in synthetic data. But this whole discussion about features and what features you can pick up points out implicitly that different data sets will have different types of features which are important to the task they're trying to do. And it might be that those particular archives of data sets you're using, it might be that none of those data sets actually have the kinds of feature patterns which might be really useful in some specific robotics task that you're interested in doing. So it might be the case that none of those data sets from those archives have data where the time difference between features is important to determination of the outcome. So I think it is, this whole question of what kinds of features am I looking for is very important. And it might be that, you either need to go to your specific robotics task, or you need to create synthetic data to be able to find data sets which show some kind of feature set which is really useful, but just doesn't happen to be in those archives that you're using.
Yeah, actually we used on this archive on this benchmark ensemble because we extended a state-of-the-art method which is evaluate on this benchmark, so that's why we have to use this archive.
Just because just because some particular method you've come up with doesn't work on anything, doesn't work particularly well on anything in that archive, doesn't mean it's useless. It might well mean that the archive is just not appropriate for testing that method.
That's.
But Ross, it sounds like a kind of almost like a fundamental problem of all machine learning, right? Because like whenever we develop methods, we sort of have no idea how useful in general it's going to be. Even so, still we somehow need to try to test this, right? Because we would like to have methods that work, that generally work, but that's sort of.
Yeah, and that's my usual shtick, is about context. So my day job is in doing modeling for money, and what you're interested in is I want some model that works for some particular problem, and it's generally the case that you're not going to find something which is exceptionally good across everything, and so if you're working from these archives, what you might be tempted to do is to say, what's my average accuracy across some archive? But it's what you're doing implicitly by doing that is assuming that the distribution of importance of features across that archive is representative of the distribution of importance of features across real world problems that you're going to apply it to. It's a really hard problem. In general, if you really care about some practical problem, then you need to have a very specific set of problems. But then as a scientist, you're saying, well, you've shown that this works on this very specific problem, but does it work in general? Well, from a practical point of view, the concept of in general is close to non-existent because the world consists of all these really specific problems. And I'm very wary about trying to average across some set of problems, because I really don't know whether they're representative of the real world that I'm likely to encounter in my specific problems.
That's true. And in addition to these data sets here, the diversity is really high. So there are some really, really small data sets, and it's somehow impossible to learn from just 10 examples and test it on 50 examples. So sometimes the range is like that. So
yeah, I came across a paper decades ago. I ended up quoting it in my research. It was about theoretical development, but their point was about context. They're saying if I've got two theories, they're saying that it's not particularly productive to say, is theory A better than theory B? They were saying that the more productive question to ask is, under what circumstances is theory A better than theory B? So the equivalent here would be to say, and you are doing this in some of your talk, you're saying, okay, we can see here's some data sets in which HTC mini rocket works better than mini rocket, or here's some data sets in which having high values of S works better than having low values of S. Then what you want to do is to say, how can I characterize those data sets? So I can say, aha, it turns out that if the data set has these sorts of properties, then I'm better doing this. But if the data set has those sort of properties, then it's better doing the other thing. And that's then basically essentially starting to explain why it is that a particular method works in particular circumstances, what it's well suited to.
But to me, this sounds as an extremely difficult task. At least nothing. I was thinking about exactly this, but I mean, nothing comes to my mind about existing methods. Just looking at the data, I mean, it's like you need to do some kind of meta description of the data to understand which method is better.
Yeah, and basically to you know, if somebody just gives you a data set and says, here's some data, I'm not going to tell you anything about it, it's just the data, which method will be better? I mean, you really can't. I mean, because basically you have to be able to characterize the data in terms of meaningful features and things first before you can say, aha, this is a type X data set as opposed to a type Y data set. So now I know to use, you know, type P method rather than type Q method. So effectively, the only way you know you've done the right thing is to be able to get good results from it.
One thing that comes to my mind, so it's kind of inspired by our previous project working with biomedical signals. I mean, in the area of, for example, ECG analysis. So they, I mean, one of their approaches is kind of to try all different, like as many methods for feature selection as possible, and then see whichever feature works best, so to say. But then you end up in such cases where you have, like, I don't know, hundreds of features being extracted, and I don't know. But at least it sounds like a kind of systematic way. So you have like full set of methods for extracting features. You try all of them and say, okay, so most likely it looks. I mean, this data set belongs to this or that class.
But as a person who was actually doing that, I can say that it's not fun.
Yes, of course, yes. But I mean, that was that's why I say it's difficult.
Oh yeah, I mean, that's the classical method that's used in my day job. I mean, literally, you'll create tens of thousands of features of some data set, and try analyzing it to see what works best. And those sorts of projects, you know, tend to turn into 6 to 9 months of full-time effort. It's unpleasant.
Yeah. Okay, so but Kenny has all time at his disposal, so until the end of PhD to try these methods.
Oh, yeah.
Okay, cool. Shall we wrap up today's session? What do you think? So, do we have any more questions? Okay, cool. All right. Thank you all for attending, and thank you, Kenny, for giving this talk to us. Really great talk. So thanks, everybody. So we see each other next time. Please check the website for the schedule. Yes. Bye, everybody. Thank you.
Bye.